the demultiplexing of this AD7 to AD0 line is done as shown in this diagram. So, this 8085, this A8 to A15. So, these lines they continually hold the higher order address bus for 3 clock cycles. Then in the first clock cycle of the memory access, so these lines the A7 to A0. So, those bits are put onto these pins AD7 to AD0, and simultaneously this ALE signal is generated. So, externally we use an 8 bit latch to store the values of A7 to A0 into this latch, and from this latch these lines A7 to A0. So, we get a clear value here, because after the first clock cycle this ALE signal will be taken off. As a result, whatever value that was latched here in the first clock cycle, they will remain here for the remaining 2 clock cycles. So, you get a clear A0 to A7 value here. So, this A8 to A15 is there for 3 clock cycles, and A0 to A7 is also there for 3 clock cycles. And now, the memory getting this the 16 bit address. So, it can generate this value, the memory location content in D7 to D0, and it will be connected to the data bus line. So, that way this or if it is that the memory, the processor is trying to write something. So, it can put the values of D0 to D7 onto the data bus onto these multiplexed pins now, but ALE is not generated. So, it will be available on this D0 to D7. So, the ALE operates as a pulse during the clock cycle T1, the first clock cycle, and we will be able to latch the address, and then when the ALE signal goes low, the address is saved in this AD7 to 0 line, and that can be used for their purpose as bidirectional data line. So, we can use this after it has been latched. So, this part is free to act as the data bus. So, the overall picture. So, how does it look like? So, the memory and this processor 8085 like that. So, from 8085, so we have got, suppose we have got a memory chip which is 1 kilobyte chip. So, this memory chip is there are 1 kilo location, and each location is 8 bit wide, fine. So, since it is 1 kilobyte memory, so that means I need 10 address lines to access individual locations within this chip. So, it is A0 to A9. So, they are actually needed for accessing this particular memory, because this memory has got 10 bit address line. So, out of that say this A0 to A7 will come from this latch, and here A8 to A15 are going. So, from there I need to connect A8 and A9. So, those 2 bits will be coming from here, 8 bits will come from here, totally making it 10 bits here, A0 to A9 they will come here. The remaining lines A10 to A15, they will be fed to some chip selection logic circuitry. So, as we have discussed in that memory interfacing classes, there we can have some sort of decoder by which we can generate appropriate chip select signal for this chip. So, whatever be the address range in which we want to put this chip, accordingly we can connect this decoder output to the chip select line of the chip of the memory chip. So, accordingly in that address range, so this memory will get selected. Now, as far as this AD7 to AD0 line is concerned, so this is bidirectional. So, though it is not shown here explicitly, but this is a bidirectional line because the data bus is also there. So, this so initially this A0 to A7 will come here, the latch will latch it, so that you get it here, but the data bus will be connected this D0 to D7 line. So, you will get you can think that I am getting a clean data bus line here, because the address bus has been separated out at this point. So, this is straightway connected to the data bits of the memory chip. Okay. So, and also we need to access this chip when it is doing a memory read operation or a memory write operation. Accordingly, this RAM chip, so it has got a read bar control and a write bar control. If you are trying to read something from the memory, then this read bar line should be made 0. If you are trying to write something onto this memory, then this write bar line should be made 0. How these lines are generated? So, these are generated by doing this read bar and IOM bar. So, these 2 lines are inverted and then it is NANDed. So, accordingly we get the memory read bar line. So, that will go to the read bar connection here. Similarly, this right bar line and this IO M bar line, so when they are NANDed, they are inverted and then NANDed, and then that generates this memory right bar signal, and that goes to the right bar line of the memory. So, this way this chip can be interfaced with the 8085 processor. So, if you have got multiple such chips, then this chip selection circuitry will become more complex. Accordingly, a number of chip select signals will be generated and they will be given to various various memory chips. Next, we will look into the instructions of 8085. So, as to use any microprocessor, we need to understand a few things. The first one we have already seen is the set of general purpose registers that the processor supports, that B, C, D, H, L in case of 8085. So, that is one thing. Second thing that we need to know is the set of instructions. Okay. So, what are the instructions that are supported? So, these two things taken together is known as the processor programming model, or PPM in short. So, processor programming model. So, whenever I am coming across a new processor, a new microprocessor, so I should try to learn what is the processor programming model for this microprocessor. Once I know that, I will know about the resources that I have, I will know the instructions that I have in my hand, and accordingly I can write down the programs for that microprocessor. So, since 8085 is an 8-bit device, it can have only 2 power 8 instructions. However, we have already seen that it uses only 246 combinations, and that represents a total of 74 instructions only, and most of the instructions have more than one format naturally. So, 74 instructions and they are using 246 combinations. So, naturally each instruction may have more than one format. Okay. And if you do a grouping of the instruction, they can be grouped into 5 different categories: data transfer, arithmetic operation, logic operation, branch operation, and machine control operation. So, data transfer operations, so they will talk how to transfer data between CPU registers, between memory locations, between CPU register and memory locations, like that, how the data can be transferred from one position, one storage to another storage. Okay. One storage location to another storage location. Then the arithmetic operation, they will tell the arithmetic operations that we can do. Logic operations will be talking about the logic things like AND or NAND or etc. Then the branch operations, so they are actually for transferring control. Like if you, in a program you are trying to implement a loop, or you are trying to implement an if then else type of structure in an assembly language program, then you will need these branch operations, in which you have to jump from one location to the other based on some condition. So, that way the branch operations will come into utility. And there are some machine control operations by which you can control the way this the processor behaves. Okay. So, we will see them later. So, each instruction can be thought of to be consisting of 2 parts. The first part talks about the task or operation that we want to perform, and this is called the opcode part. So, opcode, the word stands for operation code. So, this part tells us like what is the operation that I want to do, and the second part is called the operand. So, so what is the on which data we want to do that operation. So, that is the operand. And as we have seen that there are 246 different combinations that are supported by 8085 for only 74 different instructions. So, the 74 are the 74 different opcodes that is supported by the 8085 processor, and by looking into different type of operands that are possible, so that number reaches 246. So, for same opcode, by varying these operands, so we can get different instructions. So, first group of instruction is the move is the data transfer operation. So, you want to copy the data from source to the destination. Like you can say that this instruction like move, MOV stands for move, shorthand for move, then MVI move immediate, then LDA which is load accumulator, and there is STA which is store accumulator. So, what do? They transfer between registers, like this move instruction, like you can say move B comma C. So, you can have an instruction like say move B comma C. So, what it means, the content of this C register will be moved to the B register, or you can have MVI, the move immediate B comma 1 byte can be specified, say 56. So, that means I want to move the value 56 into the B register. So, in this way I can talk about various operations that we can do in various movements that we can do in 8085. Similarly, there is this LDA and STA instructions. So, this LDA and STA instructions, so they talk about how to move values to the accumulator. Okay. So, you can from memory location, so you can load the value into accumulator. So, there is this LDA instruction is something like this, LDA 1000. So, it essentially means that accumulator will get the content of memory location 1000. So, it will get the content of memory location 1000. Similarly, you have got STA, say STA 2 or 2000. So, it means that the memory location 2000 will get the content of the accumulator register. So, this way I can have this data transferred between accumulator and memory locations, or you can even there are some more instructions. So, that we will see later. So, the other registers can also be used for similar purpose for doing this data transfer from memory to CPU registers, and between registers we have got move instruction. So, so move instruction is for between memory locations and between memory location from between CPU registers or CPU register and memory, whereas LDA is for LDA and STA, these are special. So, these are with respect to accumulator only, and this MVI is for immediate. So, if you want to move some constant value to some register, so you can use this MVI instruction. The data in the source is not changed. So, all these move instructions or the load or store instruction, the source from where the data is being moved, so that is not changed. So, in some sense this is not a move, this is basically a copy operation. Okay. So, that is why it is said that it is simply a copy operation. So, the next instruction that we will look into is a special instruction which is called LXI. So, it says that it is load extended immediate. So, load extended immediate is LXI. So, this is for loading 16-bit value onto some register pair. So, the format is like this, LXI RP some 16-bit value. So, it means that so in that register pair we will load this 16-bit value directly. So, typical example is say LXI B 4000 hex. So, so when I say 4000 and H at the end, so that means I am talking about a hexadecimal number. So, in assembly language programs, so normally that is the custom followed. So, if you follow a number by the character H, that means it is a hexadecimal number, otherwise it is taken as a decimal number. Of course, it can vary from assembler to assembler, but this is some common convention that is used in most of the assemblers. So, this 4000 hex, this value will be moved on to this B register pair. So, B and C form a 16-bit register pair. So, this 4000 number will go to the pair BC, and out of that this 40 being the higher order byte will go to the higher register, that is B register, and this 00 being the lower order byte will go to the lower register. So, upper 2 digits are placed in the first register of the pair and the lower 2 digits are placed in the second register of the pair. So, that is the LXI operation. Then once this LXI has been learnt, so we can talk about another very interesting operation or another very interesting type of register, which is called memory register. So, what it means is that you can treat as if some memory location as a register also. like most of the instructions in 8085 can cause a memory location, can use a memory location in place of a register. Typical example is move m comma b. Okay. So, what it means is that we want to copy the from data register B into a memory location. So, the data from B register will be copied into memory location M, but what is this memory location M? So, this is basically indicated by the HL pair. So, HL pair, suppose this HL pair contains the value 2000. So, in that case that HL pair value will be used as a pointer, and that and the location content of that particular location will get modified. So, if HL pair contains the value 2000, then the memory location 2000 will get a copy of the value of register B. So, that way it becomes a technique by which you can implement pointers. Okay. So, you can use the HL pair as the pointer. So, apart from HL, so this HL pair is modified by that LXI H type of instruction. So, or so you can also use other registers for that. Okay. So, you can say that you can use an instruction to that LXI that move a comma m, that instruction, the previous instruction that we are talking, move m comma b, or when you are the m is the operand, then it is the HL pair which acts as the pointer. So, if you want that if you want to use some other register pair as the pointer, you can do that by using this LDAX instruction. So, LDAX RP, so this means the load accumulator extended, and whose location is pointed to by this RP. So, you can have LDAX B or LDAX D. So, that way you can say that. So, if you say LDAX B, the operation is that the accumulator will get the content of this memory location pointed to by the BC pair. If it is LDAX D, that means the accumulator will get the content of memory location pointed to by the DE pair, but it will not accept HL pair. So, LDAX H is not a valid instruction. Okay, it does not accept the HL pair. So, HL pair is used for indirect access by which you can get the content of some memory location into some register, and this LDAX is another indirect access where this content of B and BC and DE pairs, they can be used as the indirect address. So, this gives rise to something called the indirect addressing mode. So, without it is actually we use the data from the memory directly, and we do not load it into the CPU registers. So, for doing the addition and all these operations, so it is required that the two operands we have to give two operands. Now, this one possibility, the operands are in the CPU registers, but if you do not do that, so you can get the second operand from the memory as well. So, this is called indirect addressing. So, this uses data in a register pair as a 16-bit address to identify the memory location being accessed. So, if you are using HL pair, then it is with register M. So, it is whenever you are telling this register as M, so it is the HL pair, and if it is BC or DE pair, then you have to use you have to load the value into the accumulator and then do the arithmetic operation. So, this addition operation, like say add or add immediate. So, any 8-bit number can be added. Okay. So, the content of this add instruction. So, naturally it operates on 8-bit data, and one operand is the accumulator, the other operand is the operand that we have specified. For example, you can say like say add, add B. So, which means that the A register will get A plus B. So, this is possible, or you can say add immediate 5. So, that means the A register will get A plus 5. So, this way we can have this immediate operands, and we can have this addition of numbers. So, other possibility that we have is that we can have the subtraction operation. So, the subtraction operation is similar to addition, but it will be subtracting the number from one from the other, the second operand from the first operand, and otherwise it is same as the thing. So, it can be subtract from the accumulator and the result is stored in the accumulator. So, we both add and sub instruction, the destination is the accumulator. So, of the second source operand may be something else, but the destination is always the accumulator. So, if you are trying to use the memory as one of the operand, then first of all you need to ensure that the HL pair points to the correct memory location which will be used in the instruction for the addition, subtraction, etc. So, you can have this add m instruction. So, add m, what it will do? It will add the content of memory location pointed to by HL register with the content of accumulator, and the result will be stored in the accumulator. Similarly, we have sub m, which will subtract the value of memory location pointed to by HL from A register, and the value will be stored in the accumulator. Similarly, we have INR m, increment m, decrement m. So, these are also possible. So, HL pair will be used as the indirect address. So, other operations, other arithmetic operation, like we have to have this increment decrement operation. So, you can do it directly with respect to some register or memory location, and you do not need to disturb the accumulator. So, other operation like add operation, sub operation, what is happening is that the result is stored in the accumulator, and now suppose I just need to increment b. So, if this is not possible directly, then what will be required is that b content will come to the accumulator, then it will be incremented and the value will be stored back to the b register. So, that will destroy the previous content of a register. So, which is not always advisable for a program, that will make the control flow difficult. So, what is better is that for this increment decrement operation, we do not involve the accumulator directly until and unless it is explicitly specified that INR A, where I want to increment the A register itself. But I can, if I have got this register specified directly like INR B, INR C, DCR D, like that, then they should be done directly without affecting the accumulator. Now, how to manipulate this address part? Like we have got this register pair to hold this address, that is fine, but how can we change it? Can we change the content of this register pair? So, this is possible by using this instruction INX. So, when it is X, it is extended. So, extended means it is 16 bit. Okay. And you remember that 8085 is an 8 bit processor because it generally operates on 8 bit data. So, it is not that it cannot operate on 16 bit data, but internal implementation wise it is all 8 bit. So, that is why this is an 8 bit processor. So, this register pair INX RP, so this register pair will be incremented by 1, and this DCX RP will decrement this register pair by 1, and we do not need to worry like this RP register pairs, suppose this BC. So, when this C value becomes equal to 0 and you decrement it further, then a carry is being generated and it is automatically taken care of. So, we do not need to, if this INX and DCX instructions were not there, then you need to write an elaborate routine by which you can do this 16 bit increment decrement operations, but that is not necessary because these instructions are there, this INX and DCX operation. Now, there are logic operations. So, after this arithmetic operations, so we have got logic operations and we have got these instructions like AND. So, this ANA, then ANI. So, ANA is the logical AND operation, ANI is AND immediate, ORA is OR accumulator, ORI is OR accumulator with some immediate value. Then we have got XRA for the XOR operation and XRI for again XOR operation with some immediate operand. So, we have got this source as accumulator and we have got 8 bit number. So, that is the content of a register or content of memory location as the second operand, and the destination is always the accumulator. So, otherwise they remain same. So, another operand, the operation that is there in logic category, that is the complement. So, this complement operation, so this is one's complement of the content of the accumulator. So, it will just invert all the bits of the accumulator. So, as such, so no other operand need to be specified. So, this is zero operand instruction because the operand is implicit. Okay. So, this is CMA complement accumulator. So, it is a one's complement, is not two's complement. So, you should not take that if I do this I will get a negative of a number. So, it is just bitwise logical operation, that is why it is not an arithmetic operation, it is a logical operation. So, it will be complementing the bits of individual of the accumulator register. Other logic operations, so we have got the rotate instruction. So, it will rotate the content of accumulator one position to the left or right. So, we have got two categories, one is rotate left, another is rotate right, RL and RR. Now, this when we do this rotate left, then this rotate the accumulator left, bit 7 will of the accumulator will go to bit 0 and the carry flag. So, bit 7 will go to bit 0 as well as the carry flag. So, it is RLC stands for rotate left with carry, and then this one, this RAL. So, it will also rotate the accumulator left through the carry. So, it is with carry and this is it is through the carry. So, in this case the bit 7 will go to the carry and the carry will go to bit 0. Okay. So, this is RLC and RAL. Similarly, we have got RRC and RAR. RRC is same as RLC, but now it is right. So, it is rotate the accumulator right, bit 0 goes to bit 7 and the carry flag, and RAR it will rotate the accumulator through the carry, accumulator right through the carry, bit 0 goes to the carry and the carry goes to bit 7.